Welcome to my channel on chemistry lessons. Make sure you like and subscribe. This is a BTEC Applied Science lesson and it's Unit 5 Chemistry, and it looks at the sigma and pi bonding. And in order to do that, we're going to look at the hybridization of orbitals. So this is part of learning A2 in Unit 5. And here we are down here, we're looking at the sigma and pi bonding in alkanes and alkenes. And also we're going to double it up with hybridization. So before we do this then, we're going to look at some prior knowledge that would come from your first year chemistry unit. Carbon will always form 4 covalent bonds. It has 4 electrons in the outer shell and it has 4 electrons that it's able to share to form 4 covalent bonds. Now the definition for a covalent bond is the electrostatic attraction between a shared pair of electrons and 2 nuclei. Reminding you of our work on electron orbitals, the shape of an s orbital is spherical. So if we were asked to draw the shape of an s orbital, we would simply draw a sphere or a circle for 3D. And p orbitals were dumbbell shaped. You may recall that you drew them like this, and there were in fact 3. You had an x, a y, and the z. So if we try and draw it 3D there, so you had a px, a py, and then this pz is represented by going into the page and out of the page. So it's a 3D. We had 3 p orbitals. So the main points for this section then. We're going to see that covalent bonds can be classed as either sigma or pi. So there's actually 2 types of covalent bond. Single bonds are always going to be sigma bonds. And if there's a double bond, it means that one of the bonds is a sigma bond and the second bond is a pi bond. So it's not 2 identical bonds when we have a double bond. It's in fact 1 sigma and 1 pi. Sigma bonds, this is when the shared pair of electrons are directly between the 2 nuclei. A pi bond is when the shared pair of electrons is not directly between the 2 nuclei and is in fact above and below the 2 nuclei. Okay, so let's take a look at the molecules ethane and ethene. So ethane is a carbon bonded to a carbon, and there's 3 hydrogens on each carbon. So each carbon has 3 single bonded hydrogens and a single carbon-carbon bond. So every bond in ethane is in fact a sigma bond. Ethene is a slightly different story though. There's a double bond between the 2 carbons, hence the term alkene or ethene. That means that each carbon that's got the double bond only has 2 hydrogens. So all of these carbon-hydrogen bonds are still the same sigma bonds, so they're still sigma bonds. However, the bonds between the 2 carbons, one of those bonds is classed as a sigma bond and the other bond is classed as a pi bond. So there's 1 sigma and 1 pi bond. Okay, so now we're going to look at the hybridization of orbitals. I'm going to start with the Sp2 hybridization, which is the type of hybridization we see in alkanes. So when we're looking at just single bonds. Now, firstly, I'm going to remind you of the electron configuration of carbon. It's a 1s2, 2s2, and 2p2. And we would show 2 electrons in the 1s subshell. We'd see 2 electrons in the 2s subshell, and then we'd have 2 unpaired electrons in the p subshell. Now the issue here is, as things stand, there's only 2 electrons that are able to undergo covalent bonding here. There's only 2 single electrons that can be paired up to form bonds. So it looks like it could only form 2 covalent bonds, but we actually know that carbon will form 4. So what happens? Well, what happens is these 2s and these 2p So this one orbital here and these three orbitals here will hybridize. Now hybridize means to change, they combine together. Hence the term sp3. That means there's one s orbital and three p orbitals. So 1s, 1, 2, 3 p orbitals. So what happens is they will combine and hybridize to make 4 new orbitals. Notice the energy, they're slightly below the 2p, but definitely above the 2s because it's a combination of the two. You could argue that it's 75% 2p and 25% 2s. So there's our 4 new orbitals, and we call these orbitals sp3 hybridized orbitals. And those 4 electrons, so this 1, 2, 3, 4 electrons, they are now all unpaired in the sp3 hybridized orbitals, and that's now able to form 4 single covalent bonds. Now the shape of an sp3 orbital, it's kind of similar to your dumbbell shape, but not quite. And this is where these orbitals now can overlap directly between. And what I'm showing with these solid red spheres is the nuclei of the two. And what can happen is these two sp3 hybridized orbitals can overlap directly between the two nuclei, and that forms a sigma covalent bond, and it's a single sigma covalent bond. And that can happen 4 times, and hence the shape around a carbon that has 4 single bonds, these 4 sigmas will form and repel as far away from each other as possible, and the shape ends up being, or the bond angle is 109.5 degrees, and it's tetrahedral in shape. Again, that's a little bit of remembering from last year or going back to last year. But there's your 4 orbitals, or your 4 hybridized orbitals, sp3, repelling equally, forming 4 sigma bonds, and the bond angle would be 109.5. Let's look at the sp2 hybridization then. So again, 1s2, 2s2, 2p2, we'd have the same electron configuration for carbon. This time though, the sp2 hybridization, the hybridization involves this one orbital, hence s, and it only contains 2 of these orbitals. So we only get the hybridization of 3 orbitals here. So hence sp2. It's 2 of the p orbitals and 1 of the s orbitals, sp2 hybridization. And that will look like this. 1, 2, 3 electrons. So you'll notice that there is one orbital that nothing's happened to it. So this 2p orbital will still be there. So we have a 2p orbital, and then we have 3 sp2 orbitals. And there's our 4 electrons. So in this situation, we have 3 hybridized orbitals that can form sigma bonds in a very similar way to we saw with sp3. So very, very similar shapes. They can overlap directly between the 2 nuclei to form a sigma bond. So these sp2 hybridized will form sigma bonds. But what ends up happening is, so let me draw a carbon now with 1, 2, 3, 1, 2, 3. So we've got 3 sigma bonds on each carbon. The bond angle this time for those 3 is now 120 degrees. So the bond angle is different in an alkene. And the shape is classed as trigonal planar. Again, that's just recalling facts from back into your first year chemistry topics. So it's a different shape. So where's this pi bond then? Where's this pi bond coming from? What happens to the pi bond? And the pi bond comes from this p orbital. Now, the p orbitals are dumbbell shaped, so we still have one p orbital on each of the carbons. So there's still a p orbital with an electron in. And what happens is these p orbitals actually overlap. So these p orbitals will overlap. So we'll end up with the overlap of p orbitals below and above. And this is our pi bond. So a pi bond is formed from the overlap of the two p orbitals. So the bonding between the two carbons is a sigma bond from the sp2 hybridized orbitals and a pi bond. And that's the end of this lesson. Hopefully you found that useful. If you did, please make sure you like and subscribe.